Hello, and welcome to Math 120 Final Exam Review, Roots, Radicals, and Exponents. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. This particular review is geared towards Doña Ana Community College, Math 120, Intermediate Algebra. The review that I'm taking these questions from can be found at the school's website, dacc.nmsu.edu/math. In the right side menu, you'll find Final Reviews. Click there, and you'll see a list of all the course's final reviews. Math 120 is the review that we're looking at. The numbers will coincide with, the numbers in this video will coincide with the numbers on that review. Here we go. This is a no calculator problem. The exam is cut into two parts, with calculator and without. So any of these examples where I have the no calculator icon, it means you're not going to be allowed the use of a calculator on this. Don't worry, the numbers are good. They're not as bad or as difficult or as decimally as we'll find later. Yes, decimally is not a word, but I just used it. So let's look at some exponents. Simplify the following and write all answers without negative exponents. Our first problem is given to us as the quantity 5a to the fifth divided by a cubed b to the fourth to the negative 1 power. Now, I'm going to do two different things here. On this first problem, because it's a negative 1, I always think of that as reciprocal, right? The negative says take it where it isn't. If it's in the numerator, negative exponent tells you take it across the fraction bar, make it a denominator. If it's in the denominator, the negative 1 exponent tells you take it across the fraction bar, put it in the numerator. So in this one, I'm choosing to use the outer exponent first. And when I do so, I will take the original problem and I'm going to flip it. And I leave a power of 1. I didn't type it in, but it's still there. 5a to the fifth over a cubed b to the fourth to the negative 1 power is the same as, I'm going to flip my fraction over, and now I have a positive 1 exponent. But a positive 1 exponent is the best possible thing because everything that doesn't have an exponent has a positive 1 exponent. So I just have to simplify what's inside the parentheses. Here I see an a cubed in the numerator and a to the fifth in the denominator. Notice the denominator has more of them, so I know my a's will end up in the denominator. How many more? Well, here's 5 a's in the denominator, 3 in the numerator. The denominator has 2 more, so I'll have an a squared in the denominator. The 5 doesn't simplify, no other numbers, 5 in the denominator. B to the fourth, no other b's, stays in the numerator, and that answer is simplified. But in part B, I'm not going to use the negative right away. I save that for last. So it just kind of depends on the problem. You do not have to do your problems exactly like I do. That's one of the nice things about math. Many different approaches will get you to the same output. If you're struggling and you can't find a method, try mine. See how it works for you. If that doesn't work for you, that's all right. Keep searching for another way. So here we have 18m squared n to the negative 2 over 9m to the negative 4 n to the negative fifth, all to the negative 3 powers. In this one, I'm going to simplify the inside first, and then I'm going to use the exponent outside the parentheses. Why? I don't know. I just chose to. That's what occurs to me first. I always try to go with my first instincts because they're usually the best. So given my problem, 18 divided by 9 is 2 over 1. M squared and m to the negative 4. If I'm dividing two things with the same base, m, I subtract their exponents. 2 minus a negative 4 becomes 2 plus 4, which gives us m to the 6th. Dividing two things with the same base of n, using the quotient rule, n to the negative 2 minus negative 5, so negative 2 minus a negative 5 is negative 2 plus 5, which is n to the third power. I still have the negative 3 on the outside, and I still leave that 1 in the denominator because I have a fraction. I'm just going to leave it until I'm finished with the problem to know what's going on. Now, the negative of the 3 tells me everything switches around. It's the reciprocal. So I flip everything up. What was in the denominator is now in the numerator. What was in the numerator is now in the denominator. And then I use the distribution of power over a product and a quotient at the same time. And I take 1 to the third power is 1. 2 to the third power to get 8. M to the sixth to the third power, a power raised to a power we multiply, so that becomes m to the 18th. N to the third power to the third, a power raised to a power I multiply, and I get n to the 9th. Without that 1, I might not have had my fraction in the answer. I might have just forgot completely that I had a denominator. So it's a good idea to keep your fraction as long as possible, as long as you know you're going to need it. Part C. This one is hideous. Look at that. 25x to the 5th, y to the 16th, z to the negative 8 over 157, a to the 4th, b to the negative 2. 25 and 157 don't have anything in common. X, y, z, a, b, nothing's going on, but the key is right here. To the power of 0. This looks like a really hard problem, but it's the easiest one here because anything other than 0 raised to the 0 power is 1. No work needs to be done. Answer's 1. Move on. Let's simplify some radicals. We're going to assume that each variable is non-negative and write the result in radical notation. So we start with the cube root of 8m to the third n to the 7th. So the first thing I'm going to do is I'm going to rewrite 8 as 2 cubed. And then, because it's a cube root, I'm going to remove groups of 3. So I have one group of 2's that comes out with none left over. Right? There's a whole group of 3, nothing left over. I have one group of m that comes out. There's exactly 3 of them, nothing left over. I have 2 groups of n's, right? 2 groupings of 3, because 3 goes into 7 2 whole times. But there's an extra one. Right? I have a group of 3, and then another group of 3. I've taken up 6. I have 1 left over, so that's going to stay inside. What did we just say? One group of 2's that comes outside, that's 2. One group of m's that comes outside, that's m. 2 groups of n's that comes outside, that's n squared. But there's one left over, one n left over that has to stay on the inside. That's the cube root of n left on the inside. It's like you can't go anywhere until your 2 friends show up. So there's 3 of you that go at a time. You have to wait for the next person before you can get on this ride. To simplify the square root of 24, x to the 5th, y to the 12th, z, I'm going to first rewrite 24 as 4 times 6 because 4 is the largest perfect square that goes into 24. So I'm going to remove groups of 2 because of the square root. The square root of 4 is 2. The square root of 6, I don't know, so it stays inside. It doesn't have any groups of 2. 2 goes into 5 2 whole times with 1 left over. 2, right, because it's square root, goes into 12 6 times evenly. 2 does not go into 1. This z doesn't have a buddy. He can't ride the ride. He has to stay inside and wait until his partner shows up. So it's 2x squared y to the 6th times the square root of 6xz. One more of this type. The cube root of 40, a to the 6th, b to the 10th. We'll rewrite 40. Now we're looking at cube roots. The biggest perfect cube that goes into 40 is 8. We know that that's 2 cubed. We did it in problem A. So 40 can be rewritten as 2 cubed times 5. Everything else stays. So I know the cube root of 2 cubed gives me a 2. The cube root of 5, I have no idea, so it stays inside. It doesn't have partners to go with it. 3 goes into 6 2 times. 3 goes into 10 3 whole times with 1 left over, so 1 stays inside the radical. Don't forget to put your index, because if you don't write it, it's assumed to be a square root, and you don't want that. Good work, good work. Let's look at the domain for some radical functions. f of x equals 2 times the square root of x plus 3 minus 6. Thought that was a 7 for a minute. The domain of a radical function with an even root, so in this case a square root, index of 2, even root, will always be the radicand, the part under the radical, set greater than or equal to 0. We can't take the square root of a negative value. In this case, that means that x plus 3 has to be greater than or equal to 0. Subtract 3 from both sides. X is greater than or equal to negative 3, which is an awesome answer, but you can also use interval notation. Negative 3 and anything higher. Because of the or equal to, we use the square bracket. Remember, you never reach infinity, ever, so that's always a parenthesis. Similarly for part B, f of x equals 8 plus 2 square root of x minus 4. This x minus 4 under the radical, that's the radicand, has to be greater than or equal to 0. Let's add 4 to both sides. We get x is greater than or equal to 4. And we can write that in interval notation as the interval close bracket on 4 to infinity parenthesis. Same functions, but now we're going to do something different. We're going to find x such that f of x equals 0. Now, think about what that means. Find x. So I'm not replacing x. I want to know what x is. So at the very end of my answer, I'm going to have x equals. Such that, all right, so this is giving us a condition. F of x is 0. So in my function, I'm going to, instead of writing f of x, I'm going to replace that with 0. So 0 equals 2 times the square root of x plus 3 minus 6. Now I want to solve this. In order to solve just about anything, any type of equation, we want to isolate that type. So I'm going to add 6 to both sides. 6 equals 2 times the square root of x plus 3. But if I want to truly isolate that radical, I'm going to divide both sides by 2. 6 divided by 2 is 3. 2 stuff divided by 2 is just stuff. Now that I have the radical isolated, it's a square root, so I'm going to square both sides. 3 squared is 9. The square root squared leaves me the radicand. To solve for x, I'm going to subtract 3 from both sides, and I get x equals 6. Now I'm going to check this. 6 plus 3 is 9. The square root of 9 is 3. 3 times 2 is 6. 6 minus 6 is 0. It works out. Awesome. Let's try it again. F of x equals 8 plus 2 times the square root of x minus 4. We know that f of x is 0, so I'm going to replace f of x with 0. I want to isolate the radical, so I'm going to subtract 8 from both sides. And then divide both sides by 2. I get negative 4 equals the square root of x minus 4. Once I have the radical isolated, it's a square root, so I square both sides. Negative 4 squared is 16. Make sure you square that negative also. The square root squared gives us the radicand, x minus 4. When I add 4 to both sides, I get x equals 20. Let's see. X equals 20. 20 plus 3 is 23. Whatever the square root of 23 is, and I don't know off the top of my head, when I multiply it by 2, that's going to be huge. And when I subtract 6, no way is that going to be 0. So it doesn't work in the original. There's no solution. Some of you might have noticed right here, we can't have a radical, a positive root, equal to a negative value. So maybe you recognize right here, that's going to be no solution. That can't happen. If you recognize that, fantastic, great work. You could just write your answer, no solution. But if you don't recognize it, that's why we always check it in the original. See if it works. If it doesn't, 2 things. 1, there's no solution. Or 2, you messed up somewhere. So you might want to try it again, see if you get the same answer. Then you know it's no solution. All right. We can use a calculator on this one. The average forward speed for neotropical butterflies can be modeled by the function v of m equals 8.7 times the square root of m, where v of m represents the average forward body speed in meters per second, and m represents the body mass of the butterfly in grams. Use this model to estimate the average forward speed of a butterfly with a body mass of 0.5 grams. Wow. Butterflies. All right, they're flying. Here we go. What are we given? We're given the number of grams. We're given the body mass. Let me see. Body mass in grams, that's m. So we're given our m value. All we have to do is evaluate the function. The velocity of a 0.5 gram butterfly is 8.7 times the square root of 0.5. Notice, since there's not a no calculator symbol over here, we can use the calculator. Let's round that to 1 decimal place. We'll say that's about 6.2 meters per second. That's the units for our velocity. It's always a good idea to include units. According to this model, part B, what would be the body mass of a butterfly that has an average forward speed of 5 meters per second? We're going to round our answer to 1 decimal place. So we're given a speed, we're given the velocity is 5 meters per second. So we're going to replace this whole v thing on the left-hand side with 5. The whole velocity, the whole left-hand side is 5. So 5 equals 8.7 times the square root of m. To isolate m, we first divide, get the radical by itself. And I'm not going to find that number yet. I'm going to let my calculator handle this later. 5 over 8.7 is the square root of m. I have the square root isolated, so let's square both sides. 5 divided by 8.7, all squared, equals m. And that's our mass. That's what we want. So now we use our calculator. 5 divided by 8.7. I'm using parentheses just as they're typed. Then square it. We're going to call that about 0.3 grams. Let me see. 0.5 grams gives us 6.2. Smaller grams, smaller velocity. The answer makes sense. It's reasonable based on our part A answer. One more problem. Here we go. The approximation of the body length of mammals based on the mammal's body mass can be expressed through the equation L of m equals 0.330 cube root of m, where L of m represents the body length in meters of a mammal with a mass of m kilograms. Yeah, that's a mouthful. There's a lot of m's in there. Use this model to estimate the body length of a mammal with a body mass of 4.6 kilograms. I'm given kilograms. Kilograms, that's my capital M. Oh look, my capital M is 4.6. Everywhere I see an M, I put in 4.6, which means I evaluate 0.330 cube root of 4.6. Using the calculator, that's about 0.5 meters. My length is given in meters, so I include the units. Part B. With this model, estimate the body mass. So now we're going to estimate the mass. That means find m. With a body length of 1 meter. Round to 1 decimal place. So the body length, the L stuff, that gets replaced by 1. 1 equals 0.330 cube root of m. Solving radical equations. We want to isolate the radical. So we're going to divide by 0.330 on both sides. I'll end up with 1 divided by 0.330 equals the cube root of m. Now to get m by itself, since it's a cube root, I'm going to cube both sides. 1 divided by 0.330 to the third power equals m. I'll enter this in my calculator exactly as it's written, and I find that this particular mammal has a mass of 27.8 kilograms. That's it for roots, radicals, and whatever else I said that this was. What is that? Roots, radicals, and the rest. Thanks for listening.